Next, next, let's understand how to use Reynolds transport theorem when external forces are given to you in the question. So next topic is using Reynolds transport theorem for the problems where external forces are present. Okay, so this is our next task. So to start with, do you know any equation that relates external forces with your system quantities? So we have one equation which is dp system, the rate of change of linear momentum is equal to sum of all the external forces applied on the system. This we know, right? So this F is the external force applied on the system, and that equals the rate of change of linear momentum of the system. Okay, and when these external forces are 0, we say dp system by dt is 0, and that's how we get conservation of linear momentum. Okay, all right. Now what was our Reynolds transport theorem? So we had this expression from Reynolds transport theorem, right? So d by dt of n system equal to d by dt of integral over cv eta rho dv plus integral eta rho vxyz dot dA vector, where eta was total extensive property n over mass of the system, and vxyz was the velocity of fluid crossing the control surface with respect to control volume, right? And we argued that this velocity would be the velocity of the fluid minus the velocity of the fluid with respect to ground minus velocity of your control volume with respect to ground. Correct? Okay. Now this n system, this extensive property, is my linear momentum p. Okay, all right. So then what will be eta for this case? Eta will be, so let's just write it now, extensive property is linear momentum of the system, that is n is equal to p. Okay, so this implies eta would be mass times velocity of the system. And what is the velocity of the system? Velocity of the system is simply vxyz divided by mass. So this mass would cancel out with mass, and we will be left with vxyz vector. Okay, so this eta can be a vector or can be a scalar. Okay, please keep this in mind. Okay, so let's now put eta here. So this would become d p of system divided by dt equal to d by dt cv. Eta is equal to vxyz vector rho dv plus integral over control surface. Eta is vxyz vector rho vxyz vector dot dA vector. Okay, now let's see in the problem you are given that the flow is uniform and fluid is incompressible. Let's say you are given this condition. Okay, then what will happen to this expression? Let's see. So first of all, let's consider uniform flow. So if my flow is uniform, I know that over a cross section the velocity vector would remain constant, right? And this would be independent of the dA that I choose. Okay, so in that case this v vector I can take outside of the integral, and this v vector I can take outside of the integral. But let's just focus on this term and not on this term. Okay, so I can take vx y z outside of the integral. Alright, and now let's say if the flow given to me is incompressible, then what would happen? If it is incompressible, I can take rho outside of this integral. Okay, because if it is incompressible, rho is constant, and thus it would not depend upon the dA that I choose, and I can take this rho outside of integral. Similarly, if you consider this term, I can take rho outside of this integral and also outside of this derivative, since it is a constant. Okay, all right. So if these two terms are given to you, if these two conditions are given to you, let's just focus on only term 2. So what is 2 in that case? In that case 2 would become, since I can take vx y z vector outside of this integral, this would become vx y z vector, and since it is incompressible fluid, I can take rho outside. This will become cs v x y z dot dA. Okay, all right. So now can you recognize this term? Have you done some simplification for this term before? Yes, we have done it. Where we have done this? When we considered extensive property as mass, right? So when we considered mass as an extensive property, we understood that we can simplify this term like this. Right? I hope you remember this. Okay, so then I can just replace this term with this term. Okay, let me just write it. So this would become vxyz rho summation. Now there is one problem with this. Although I can take this vxyz out of this integral, but this velocity vector would be actually the velocity vector at that ith control surface, right? Okay, so it's better if I write integral over cs as integral over cs1 plus integral over cs2 plus integral over cs3 plus so on. Okay, then I can write this as rho vxyz at cs1 integral vxyz dot dA vector at that cs1 plus so on, right? So this would become summation of okay, this one will be summation vxyz dot a vector at cs1 plus rho vxyz at cs2 vxyz dot a vector at cs2 plus so on. So can I just write it like this: rho summation over csi vxyz vector rho vxyz vector dot a vector on that csi, on that ith control surface, right? Okay, so thus I can add this term, I can replace this term with this term. So let's just write it. We can add this as summation over all the control surfaces v xyz rho vxyz dot a vector, and this all is for that ith control surface. Okay, okay, and again this expression contains this rho at that csi, which means that this is for the case when multiple fluids are there with density rho at csi are there. Okay, so let's say I had this thing. Okay, I had this situation where the flow was from this pipe. Okay, now let's say the fluid which exits from this pipe has density rho 2, the fluid which exits from this cross section has density rho 3, the fluid which is entering this tube is rho 1. So in that case I can use this expression. And in case if I have only one fluid, with density rho, I can take this rho outside of the control surface, right? Okay, okay, so now let's focus on the term 1, which is this. Okay, so now if the fluid is uniform, if the flow is uniform, can I take vxyz outside of this integral, which is the integral over a control volume? And for incompressible flow, can I take rho outside of this integral? Or in other words, let's say you have a situation like this. Again, let's say you have this pipe. Okay, and let's say the fluid is flowing like this. Okay, and you have considered the control volume. Let's say this is my control volume dv with volume dv. Okay, so this is my control volume with volume dv. Now let's say if the flow is uniform, will the velocity vector be independent of the control volume that I choose? So let's say if this is my control volume dv1, let's say this is actually dv2, this is cv2. So will this be independent of this control volume that I choose in this volume? The answer is no, right? So then I cannot take this vxyz out of this integral. Okay, but in case when the fluid is incompressible, I can take rho outside of this integral because rho is constant throughout. But in case of multiple fluids, since let's say this corresponds to fluid 1, this corresponds to fluid 2, and this corresponds to fluid 3, then rho would also change depending upon the control volume that I choose, right? Okay, so then for uniform and incompressible fluid, what can I say about this term? The answer is I cannot say anything about this term. Okay, then what is the other special case you have mostly in your problems? The third case is steady state flow. Now let's say the third assumption that you have considered is the flow is steady. So if the flow is steady, del u by del t at particular coordinate xyz is 0, and also del rho by del t at particular xyz is 0. Okay, so now let's say I also have steady flow now. So then what can I say about this term now? So in the steady state flow, we know the partial derivative with respect to time is 0, but we have a full derivative sitting over here. So let's consider one. So one is d by dt vx by z rho dv, d by dt integral over control volume vx by z rho dv. Okay, this is one. All right. Now if vx by z is a function of x, y and z, and rho, okay, so rho is given that the fluid is incompressible, so rho is constant, so this won't matter. Okay, so if this is the case, then can I say that the answer I will get after integrating this thing will not be a function of x, y, z? Okay, and the integrals are from, let's say, x equal to xi to xf, y is equal to yi to yf. So depending upon the size of your control volume, you will do the integrations. So integrating some function which is dependent upon the variable x, y, z integrated over dx, dy, dz gives me an answer which is independent of x, y, z. Okay, and also since vx, y, z is not a function of t, and rho is not a function of t, and this dv also is not a function of t, can I say that this integrand cv is independent of t? Since neither of these three is dependent upon time. Why? Because I am given, so for steady, I am given that the flow is steady, right? I am given that the flow is steady, then this V is independent of time, this rho is independent of time, and this dV actually, just for clarity, let me just write it again. So what we were given? We were first given uniform flow and incompressible flow, right? Okay. So in that case, for uniform flow, we have V xyz although it is dependent upon the coordinate that you choose, but it is independent of, and it is also dependent upon time, but it is independent of cross-sectional elemental area. And incompressible flow means that rho is a constant. Okay. Now if I add another constraint that the flow is steady, then what I will have is Vxyz is just a function of x, y and z. Okay. So in that case, integral over Vxyz rho dV will become independent of time t. Okay. And thus the derivative d by dt over the Cv Vxyz rho dV, this would become 0. Okay. So for uniform, incompressible and steady state flow, this term goes to 0. Okay. So let me just again write this term after knowing 1 and 2. So this would become summation f external equal to, so the first term was 0 and the second term was summation over CSI Vxyz rho Vxyz vector, summation over CSI Vxyz dot, not dot, but Vxyz rho Vxyz vector dot A vector, and this is all for that particular control surface CSI. Okay. So this is the expression that we will get for incompressible, steady state and uniform flow. Okay. And let's say if the flow is not steady, I will get d by dt Vxyz rho dV over Cv plus this term, which is CSI Vxyz rho Vxyz dot A vector, and this is for that CSI. Okay. So this term is when your fluid is incompressible and the flow is uniform and the flow is unsteady. Okay.